Welcome back to the course in Nuclear and Medicine Physics. Today we're taking a look at simulation software to better understand nuclear medicine imaging.
Can you tell us, Barry, what the software is called, and just give us maybe a 1-minute intro to why you wrote this software?
Okay, so this software is called MSIM, and I wrote it because when I teach nuclear medicine technologists, I can't describe the mathematics of things, so I want to give them an intuition that simulates what's going on when imaging with a gamma camera. And I relearned the skills necessary for this when I restarted my neutrino research, so it's sort of a very interesting spin-off of it. And so for many years, I've worked with the problem of how to teach the imaging aspect so people get an intuition. And we'll see how far we can get before the software crashes. But what we see here is this is simulation of a SPECT camera. And for the SPECT camera, can you see the VR aspect that I just added?
Yes.
So this is a SPECT camera, and this is the image we get of a anthropomorphic phantom, a Zubel phantom, which is based on voxel man. And so this can be changed to simulate various types of tracers. And so this is a Zubel phantom arms down. And so this tracer is a representation of what we would get when we do a bone scan. So for example, with the tracer MDP, and here's what the image looks like. And so here's our camera here, here's our image, and we can change various aspects of the imaging process. So in SPECT cameras, one of the things you can change is the size of the pixel matrix. So previously we saw a 64 by 64 matrix. Now it's a 128 by 128 matrix, and we can go back. One of the powerful aspects of a simulator is you can add different physics to the image. So for example, if I want to take into account the noise, I can add the noise back into the image. And you can see that better with a larger matrix. Let's actually look at blurring instead. So this is blurring. This is if the camera is far away at distance of 33.5 centimeters. If we move it closer to the patient, let's say 15 centimeters, the blurring decreases. If we move it closer, let's say 10 centimeters, it's less blurry. And so this is one very important aspect in learning to use a gamma camera, is to move the camera closer. You can also change the lens from an all-purpose to a high-resolution collimator. Did you see that the resolution changed?
Yes.
Go back again, all-purpose, blurrier, high resolution. I'll go to an ultra-high resolution.
Very nice. Yeah.
Same distance, collimator change. You can see the effects of that. Now, if this is working, we can also do this for SPECT. And in SPECT, what we're going to do is set up an acquisition. Here, we're just going to use a single detector. And so you see the SPECT camera here. It's going to acquire, the gantry is going to move 360 degrees around the patient because we're just simulating a single detector. And we want 64 stops. Actually, no, sorry, we want it, let's just do this setting. Now it crashed when I tried to do 2 detectors. Oh, there we go. That works now. So we're going to have the gantry move 32 angles around the patient for a total of 64 frames. The detectors are oriented 180 degrees from each other. I'm going to try and move these a little bit closer.
Why is it that you have 32 stops but 64 total? Is that because you have 2 heads?
Yeah, because one head does 32 of them. The other head does 32 of them, 64 detector. So let's see if this works. So we set up how much activity. You see that it's going to, this is simulating stopping after 30 seconds. We've got a 128 by 128 matrix. And so this is simulating the acquisition. Now, these are not stored images. The only, what this is doing is it's a direct calculation from the 3D voxel distribution. So it's doing a line integral with attenuation through the body.
It's an analytic. It's an analytic model that tries to capture the physics, I guess.
It captures the physics, and it can accurately capture the physics of blurring, attenuation, and noise. So I'm not going to go through all those. I just want to get to the spec part, the reconstruction part. So here's our data set. Here's the different frames. We can often view this in spec by making a movie of showing one frame after the other, like this. Now, this is not your pet MIP. This is just one frame after the other.
Yeah, it's not an image in the reconstructed sense. This is a projection images as you're rotating around the patient.
Yeah, this is just one planar image. These are just planar images at different angles.
Yep.
Now, it sounds like you've learned about synograms. We can also view this as a synogram, or the different synograms. So these are the different, this is the synogram for pixel row 64 of the image. So we can look at the different synograms. And if you're not familiar with what a synogram is, here's a demo that I made of a synogram. So here is one frame. If we look at this one pixel row at this one angle, this is I guess this would be an anterior view. That pixel row is placed, it's cut out and put into this bottom row of the synogram. For a different angle, now the frame's at a different angle, the same pixel row is put into a different row of the synogram. And so each angle, the same pixel row is put into a different row in the synogram. So the synogram is the same pixel row, this one, in the different frames.
Yep. Yep, and we showed an example in a lecture where if you look at it just a point source and you do this, you will see these sinusoidal curves, which you're sort of seeing here too, even though this is not a point source, but you sort of see it for the hot point especially. So that's why it's called a sinogram.
Yeah. And so when we do reconstruction and inspect, we have to first we have to reformat the data from frames into sinograms, because sinograms are the basic unit that are reconstructed. So let's do that. Let's look at reconstruction. So what we're going to do is we're going to reconstruct a slice. And I'm just going to do a demo of this. So we're going to demo filtered back projection. And so we're going to be using just a Ramlack filter. And so we're going to do the demo of reconstruction. So here's how reconstruction works if things are going properly. Okay, so just pull this aside. So here's a sinogram that we're going to reconstruct. Here is the pixel row that from the frame that was acquired at 0 degrees. What we do is we take that pixel row and we take the counts and we evenly distribute them back over the image. That's what this is, at that angle. So we take these counts. We don't know where to add them back into the image, so we just do the maximum ignorance thing and add them back into these voxels. So we back project the counts over the image at 0 degrees. Okay, so this is what it looks like if we use unfiltered projection. So if we don't apply the ramp filter, this is what it looks like for that angle if we do the filtered projections. Now, if we do the second row of the sinogram, you see it highlighted here a little bit. That was acquired at 5.6 degrees, so we back project that at 5.6 degrees. That's what the individual back projection looks like. This is what it looks like when we sum the first back projection and the second back projection. And so these are if we don't filter the projections with the ramp filter, which is required for filtered back projection. These are what they look like when we've done the ramp filtering. So this is after 2 back projections. That is the first 2 rows in the Synogram. If we do it again, here's the third one. This is what the individual back projection looks like. This is what it looks like when we add the first 3. And this is what it looks like if we've done the ramp filtering. This is what it looks like for 4. And then let's just let the movie run. So you see, I hope you can see that we're back projecting different pixel rows in the Synogram. This is what it looks like when we've back projected it, just the 1 row. This is what it looks like when we add together all the back projections. And so now it's gone through half of the Synograms. That's from 0 to 180 degrees. Now it's going from 180 to 360 degrees. And this is what it looks like when we didn't use the ramp filter. And this is what it looks like when we've done the ramp filtering. And this is without noise. If we had more time, I could show you what it looks like when we have noise in the data. This is just showing the reconstruction itself.
So as we were saying in a previous class, if you do simple back projection, you're really oversampling the low frequencies. And therefore, the top right image gives you a very blurry image because you're emphasizing the low frequencies overly. Whereas the ramp filter tries to do it right and get it right and put more emphasis, increasing emphasis on the higher frequencies. And through the projection slice theorem, you sort of start to see why it works. And then so you sort of start to get the image at the bottom right. Now, Barry, somebody might be surprised when they see the image at the bottom right because you see all these little artifacts and all kinds of things inside and also outside of the image, in the bottom right image, the filter back projection.
Yeah.
Can you explain, what that is and why we get those kind of things? And I guess what we do. Yeah.
So the theory of reconstruction requires that you acquire an infinite number of angles.
Right. And
the higher the resolution, the data, the more angles you need. Now, we didn't acquire enough angles.
Yeah.
Let me reconstruct. Let's see if I can get the blurry data. Blurry data requires less number of angles. I think this is going to work. Let's see. I'm not sure whether this is incorporating the blurry data.
Right.
Hold on. Oops, something else just popped up. With the blurry data, you don't need as many angles. And it may not be incorporating that, so this may not be as good. If I acquired 128 angles, which are not
exactly
for time's sake,
it would look better. It would look
better.
Yep, exactly. Thank you for that. Yeah.
And I can blur the image artificially by using a Ramlack filter or by using a smooth cutoff filter. And that would blur it a little bit so that you don't need as many angles. Does this one look any better? Maybe not. I mean, I'll put that in the demo. Anyways, so these are leftover counts. That's also the effect of noise. So in this case, it's not noise, but noise also causes these streaks. Just one thing about the ramp filter, the Ramlack filter. The Ramlack filter is actually just second-year calculus that people forgot. If you've done second-year calculus, are you familiar with the term the Jacobian of transformation? If you're going between polar and rectilinear coordinates, anybody remember the term Jacobian of transform in second-year calculus?
I think they should, because actually in a previous lecture, we did explicitly mention that Jacobian leads to the leads to the ramp filter. Yeah.
Okay, good. Well, let me just do one last one, and that is an example of OSCM. Actually, maybe I'll do MLEM first. Oh, sorry, I shouldn't have stopped it midway. It's going crazy now. Let me just let it finish. Hold on. So just ignore this for a minute. I'll pull that off screen. Okay, so now we're going to demo MLEM reconstruction. So how iterative reconstruction works. So let's just start this and set this up. So iterative reconstruction uses a loop in which it starts off with a guess of the image. It forward projects the guess of the image. It compares it with the measured sinogram. And then by some comparison method, it comes up with a new sinogram, which takes into account the difference between the forward projected sinogram. And then when you back project that, you get a new version of the current iterative image. So the initial image you start with frequently in MLEM is a uniform, so non-zero count density. So imagine just having one count, having voxel values of 1 everywhere. So that's what I've done here. If we forward project that, this is what the forward projected sinogram of this image looks like. And you see it looks nothing like the measured image. And so when you compare them, in this case by taking the ratio, this is what you get when you back project this ratio sinogram. This gives you a new updated image. And so this now will become the current image in the loop. So what's happened is this is now was the current image. We forward projected that, compared it with the measured sinogram. We take the ratio of the two, and then when we back project that, that becomes a new image, and it gets better. So after one iteration, this is what it looks like. After 2 iterations, this is what it looks like. Now we'll continue. We'll call this the current image. And so we then forward project this, and the sinogram is beginning to look more and more like the measured sinogram. The ratio is still complex. When these get really close, this ratio should almost become uniform. And then this is what the image looks like when we back project this. So this is after iteration 3.
So if I may comment here, sorry to interrupt. We talked about different algorithms. One of the best of which is what Barry is talking about, the MLEM. If you're doing some other algorithm, they might be taking the difference between those sinograms, for example. And then you would back project that, and then you get a correction image multiplied by your previous guess, and you get the new result. But here it's the ratio, then you back project, you multiply by the previous image estimate, so now you get a new image estimate. So MLEM and we showed some diagrams, and here Bear is really showing you an actual example as you go through the iterations.
So let's let it go through a few more. So I'm just going to let it slowly update the images. And we see 2 things. One, the image gets better. Second, the forward projected sinogram looks closer to the measured sinogram. And this is becoming closer to looking uniform.
Right.
And so you also notice you don't have that horrible streaking outside the object, which we saw in filtered back projection.
Yep.
And so this will converge where the projected sinogram equals the measured sinogram, but we usually stop it before that because that will become too noisy. So this is what it looks like for 32 iterations. So it's a pretty good looking image, except it's fairly slow. We can also do this with a faster version called OSCM, which is the basis for all modern clinical spec reconstruction. What this does is, instead of using the whole data set, that is all rows in the Synogram at one time, it divides the data sets into subsets. So here we had 64 rows, but now we're dividing it into 1, 2, 3, 4, 5, 6, 7, 8 subsets, and we do sub-iterations. So what we do is we just take these rows and we compare it to the corresponding rows of the Synogram, and then we do the ratio here, and then we back project and make a new image after just one sub-iteration using only 8 of the 64 pixel rows.
So the y-axis is angles for everyone, you know, the one that goes to 64. Those are like the projection angles. So Barry is only looking at maybe an eighth of the angles and then doing an update.
And so it updates 8 times per iteration.
Right, and you're moving now the angles you're looking at. So you, at any given time, instead of looking at the entire Synogram space, you're looking at an eighth of it, for example, in this example.
And so this makes the image improve 8 times faster. And so that brings it in the realm where it's clinically viable to actually do this. So it uses the same basic methodology as MLEM, but it's 8 times faster so that it's clinically available. And so this is what it looks like after only 4 iterations with 8 subsets. It's as good as the 32 iterations of MLEM. And so that's what the basic is.
Yeah, you've done 32 updates, but you've only gone through the entire data set 4 times. So it's 8 times faster, essentially.
So here's just an example of reconstructing a large area of the patient. Let's say we want to construct frames between here and here. And I'm going to do this with filtered back projection, and I'm going to use a little bit of a low-pass filter on this. And somewhere here, I'm going to make it so you can see how quick it reconstructs. So just get rid of all this other junk. So just watch down here how long it takes to reconstruct. I'll actually do this many slices. So start reconstruction. Boom, you see how fast it's reconstructing each slice with filtered back projection? And so here's the slices. And here's the 3D data set. So you saw how fast that was with filtered back projection. But you see that you do get these streaks around the edge. They're not the best quality images. Let's try the same thing with MLEM with 32 iterations. And so we're reconstructing. Here I'm showing you the individual ones. See how much longer it takes to reconstruct the slices? I shouldn't have chosen so many. But this is actually a good example of just the basic relationship. Here's the Synogram for a part of the body, for a slice of the body. Here's what the slice looks like.
After you reconstruct it.
After you reconstruct it. So reconstruction is the great magic of transforming a Synogram into a slice. And so anything anybody wants me to try? If I was going to do this with OSCM just to show how much faster it is, but just for time's sake, maybe we could just stop there unless somebody wants me to try something.
Yeah, in fact, OSCM, I've heard it was an accidental discovery. I think it's a 1994 paper where I think I don't know the exact details of it, but I've heard that somebody just made a mistake in the code, not using the entire data set to do an update, and then suddenly it was actually working quite well. and then the rest is history.
You know, I remember when it first came out, the two investigators, Hudson and Larkin, I think,
Yeah, that's right.
they made the software freely available, and I remember downloading it, and then, of course, I lost it. So I went back a couple of months later to the website, and they were asking $5,000 a license. And it's worth it because they need to get their money's worth out of the vendors who were going to start incorporating it in their clinical software. Okay, so that's how long it takes to do the MLEM. But you see the image quality is considerably better, that you don't have all these excess counts on the outside, and they're just far better images. And I'm just going to pull this in a little bit, and then we'll do OSCM just to get a sense of how quick it is to do the OSCM. So you see that it's reconstructing almost as fast as filtered back projection.
Right. Now there's a limit to it.
So anyway, so that's...
If you use Barry, if you do use, there's a limit to this. If you use way too many subsets, then this thing it does break down. So there's a reasonable number of subsets that you have to have. So, 8, 16,
24 subsets.
24, these are numbers that people have.
Yeah, it crashed. It didn't like 24 subsets.
Okay, you try that.
32 subsets.
I've seen 21 subsets before, 16, 18.
So here's using 32 subsets. Notice you get this horizontal bias, or this vertical bias in the images, that they don't look as good as the other ones. So there is a bit of tuning you need to do of how many subsets you want and how many iterations you want.
Yep.
And so if we examine this closer, you would see that this looks a little bit more pixely, and you see a little bit of sort of streak artifacts around the edges and that. So it does require tuning to find the optimal parameters.
That's amazing. Thank you.
Questions?
Any questions? I mean, obviously people are very impressed by this software, and this really, we're very glad that we had your session after we talked about image reconstruction, because now, we are seeing, we're feeling this. We're seeing we're getting intimate with the synograms and the images, and the theory is now coming into practice and into actual individual reconstructed slices. So it's very good. Thank you very much. All right. Well, thank you, Barry. This has been an amazing session. Thank you for accepting our invitation, and for
thank you for the invitation. It's been fun.
Yeah, thank you.